A Neo-Hookean solid is a hyperelastic material model, similar to Hooke's law, that can be used for predicting the nonlinear stress-strain behavior of materials undergoing large deformations. The model was proposed by Ronald Rivlin in 1948. In contrast to linear elastic materials, the stress-strain curve of a Neo-Hookean material is not linear. Instead, the relationship between applied stress and strain is initially linear, but at a certain point the stress-strain curve will plateau. The Neo-Hookean model does not account for the dissipative release of energy as heat while straining the material, and perfect elasticity is assumed at all stages of deformation. The Neo-Hookean model is based on the statistical thermodynamics of cross-linked polymer chains and is usable for plastics and rubber-like substances. Cross-linked polymers will act in a Neo-Hookean manner because initially the polymer chains can move relative to each other when a stress is applied. However, at a certain point the polymer chains will be stretched to the maximum point that the covalent crosslinks will allow, and this will cause a dramatic increase in the elastic modulus of the material. The Neo-Hookean material model does not predict that increase in modulus at large strains and is typically accurate only for strains less than 20%. The model is also inadequate for biaxial states of stress and has been superseded by the Mooney-Rivlin model. The strain energy density function for an incompressible Neo-Hookean material is, where is a material constant, and is the first invariant of the right-Cauchy-Green deformation tensor, that is, where are the principal stretches? For three-dimensional problems the compressible Neo-Hookean material, the strain energy density function is given by where is a material constant, is the first invariant of the isochoric part of the right-Cauchy-Green deformation tensor, and is the deformation gradient. It can be shown that in 2D, the strain energy density function is where, in this case. Several alternative formulations exist for compressible Neo-Hookean materials, for example. For consistency with linear elasticity, where is the shear modulus and is the bulk modulus? Cauchy stress in terms of deformation tensors equals compressible Neo-Hookean material equals, for a compressible Rivlin Neo-Hookean material the Cauchy stress is given by where is the left Cauchy-Green deformation tensor, and for infinitesimal strains. And the Cauchy stress can be expressed as comparison with Hooke's law shows that and equals incompressible Neo-Hookean material equals, for an incompressible Neo-Hookean material with where is an undetermined pressure. Cauchy stress in terms of principal stretches equals compressible Neo-Hookean material equals, for a compressible Neo-Hookean hyperelastic material, the principal components of the Cauchy stress are given by. Therefore, the differences between the principal stresses are equals incompressible Neo-Hookean material equals, in terms of the principal stretches, the Cauchy stress differences for an incompressible hyperelastic material are given by for an incompressible Neo-Hookean material. Therefore, which gives uniaxial extension equals compressible Neo-Hookean material equals, for a compressible material undergoing uniaxial extension, the principal stretches are. Hence, the true stresses for a compressible Neo-Hookean material are given by. The stress differences are given by. If the material is unconstrained we have. Then, equating the two expressions gives a relation for as a function of, that is, or. The above equation can be solved numerically using a Newton-Raphson iterative root-finding procedure. Equals incompressible Neo-Hookean material equals under uniaxial extension, and therefore assuming no traction on the sides, so we can write where is the engineering strain. This equation is often written in alternative notation as the equation above is for the true stress. For the engineering stress the equation is for small deformations we will have. Thus, the equivalent Young's modulus of a Neo-Hookean solid in uniaxial extension is, which is in concordance with linear elasticity. Equibiaxial extension equals compressible Neo-Hookean material equals. In the case of equibiaxial extension. Therefore, the stress differences are If the material is in a state of plane stress, then and we also have a relation between and or. This equation can be solved for using Newton's method. Equals incompressible Neo-Hookean material equals, for an incompressible material, and the differences between the principal Cauchy stresses take the form. Under plane stress conditions we have pure dilation, for the case of pure dilation. Therefore, the principal Cauchy stresses for a compressible Neo-Hookean material are given by. If the material is incompressible, then and the principal stresses can be arbitrary. The figures below show that extremely high stresses are needed to achieve large triaxial extensions or compressions. Equivalently, relatively small triaxial stretch states can cause very high stresses to develop in a rubber-like material. Note also that the magnitude of the stress is quite sensitive to the bulk modulus but not to the shear modulus. Simple shear. For the case of simple shear, the deformation gradient in terms of components with respect to a reference basis is of the form. Where is the shear deformation? Therefore the left Cauchy-Green deformation tensor is equals compressible Neo-Hookean material equals, in this case. Hence the Cauchy stress is given by equals incompressible Neo-Hookean material equals, using the relation for the Cauchy stress for an incompressible Neo-Hookean material we get. Thus Neo-Hookean solid shows linear dependence of shear stresses upon shear deformation and quadratic dependence of the normal stress difference on the shear deformation. Note that the expressions for the Cauchy stress for a compressible and an incompressible Neo-Hookean material in simple shear represent the same quantity and provide a means of determining the unknown pressure. References: ABC Ogden, R.W., 1998, Nonlinear Elastic Deformations, Dover. C.W. McCosco, 1994, Rheology, Principles, Measurement and Applications, VCH Publishers, ISBN 1-56081-579-5. Gent, A.N., ed., 2001, Engineering with Rubber, Karl-Heinz Verlag, Munich. See also, hyperelastic material, strain energy density function, Mooney-Rivlin solid, finite strain theory, stress measures.